Hello, welcome back to the Machine Learning Optimized Systems seminar. Um, we're really going to begin here with we have a beautiful series of speakers coming up, and it starts today. We're very fortunate to have Sharon Lee with us. Um, Sharon, most of our speakers are going to be focused on kind of the systems building side of things, but we're lucky here to have Sharon come in from the side of the machine learning world and really a world expert in deep learning. So let me just say a moment about Sharon, and then I'll hand it over to her. And then I'll talk a little bit about logistics too in there. So Sharon is got her PhD at Cornell in 2017, and then since then has been a postdoc at Stanford. She also has worked on Google AI and Facebook AI, somewhat recently as a research scientist, and among other things was named a 30 under 30 rising star in AI and a Forbes 30 under 30 in science in 2020. So very well recognized across the world. And of course, we're very fortunate to have her joining us just this semester as a professor in the Department of Computer Sciences here at the University of Wisconsin in Madison. Just logistically here, if you need to or want to ask a question, please go ahead and just type one in the Q&A, and feel free to vote on questions that you see. We'll periodically interrupt Sharon and ask her those questions. And otherwise, I think we're ready to go. So welcome and thank you again, Sharon, for joining us here today.
Thank you, Ramsey, for the really nice introduction here. It's really my great pleasure to be here, and thanks to all of you who's here for the talk today. So today I'll be sharing with you some challenges, recent research advancement, as well as opportunities towards building ROLE, which stands for Reliable Open World Learning, especially in the presence of out-of-distribution data. So I would like to start a talk with this very simple question of how do we classify cats versus dogs, just to give you some quick background on deep learning. So nowadays, if you take a photo with your high-end camera on your phone, each channel could have up to 12 megabyte pixels. So a color image with RGB channels could easily have up to 36 million pixels. And if we take those 36 million pixels and build a fully connected networks to perform this task, say for example with 100 hidden neurons, so essentially each of those pixels is connected to all of those 100 neurons, and activation of each neuron is a weighted sum among all those pixels and followed by some nonlinear function. And one of the most commonly used nonlinear function could be rectified linear unit, in short as ReLU, which basically takes the maximum between the output and 0. And then those 100 activations then get aggregated to this output neuron, which would produce 1 for cat and 0 for dog. So if you look at this number of parameters in this network, there are 36 million multiplies 100 neurons, which is as many as 3.6 billion parameters. And that is a lot to fit on any modern GPU memory. So this is where convolutions becomes really powerful. And I would like to motivate why convolution is really useful and powerful using this example here. So this is a game called Where is Waddle? And Waddle is this character who is wearing a red and white striped hat and with this really cool glasses. So if you take this template on Waddle and then try to map to this image on the right side, you would end up finding, a lot of people who look like Waddle. And if you think about this mental process behind looking for Waddle, you're really exploiting two very important properties here. The first is translation invariance, which means it doesn't really matter where Waddle is relatively located within this image. It could be on the left side, it could be on the right side. And the second property is locality. Perhaps the nearby pixels doesn't matter so much. And this is exactly what convolution is trying to exploit. So let's look at a simple example here with an input matrix of size 3 by 3 convolved with a kernel of size 2 by 2. So this kernel can be quite analogous to this template of waddle that we just saw earlier. So essentially, this convolution would take the kernel and overlay onto one of the corner, let's say this upper left corner of this input, and perform element-wise multiplication followed by a summation. So in this example, the first output would be 0 multiplies 0, plus 1 multiplies 1, plus 3 multiplies 2, plus 4 multiplies 3, and then you get the first output, which is 19. And so when they shift this kernel by one spatial location and repeat the same process until we finish scanning this entire image. And so deep networks really, is taking this very simple basic computational unit and then add more channels to each layer with more layers, which forms a compositional structure so that the network can learn from low-level features such as the color of the fur and the texture of this, the cat fur, all the way to the high-level semantics such as a cat. And in fact, some of those architectures that you probably heard of or used before are designed in a very similar spirit of this compositional layer-wise structure. Okay, so now we're equipped with this amazing neural network architectures and training techniques, and let's try to do something cooler with it, something more complicated than simply classifying cats versus dogs. So now imagine yourself trying to build this app that can automatically classify all the images of food so that you can show users some nutrition information or even possible recipes you can make with it. And this becomes handy, especially during this pandemic time, for people like me who's been struggling with cooking, right? So to do so, we collect some training data and then train on your favorite classifier and then deploy this model. While you think you're done with all the work, more work has just begun. And why do I say that? Because in the classic machine learning literature, we assume that the training and test data distributions have to match each other. And you would hope that users would only upload photos just look like your training data on images of food. However, in reality, the training and test data distributions can be wildly different. And so in fact, in the open world, the test image can be anything beyond what you would expect. And this is perhaps one of the most valuable realizations during my previous work at industry. And this brings this fundamentally important question, which is how can we build machine learning models that function reliably in an open world? And one important step towards this goal is to be able to identify and detect out of distribution data. So for example, when this bird image comes into the food classifier that you just built, we might want to flag this image to be somewhat unusual instead of classifying into one of those food categories. And this problem of out of distribution uncertainty is even more concerning for those safety critical applications. For example, in healthcare, identify COVID from regular pneumonia based on chest X-ray scans, or in autonomous driving, trying to detect unusual objects on this road. So now let's dive into some of those challenges and see how we can better estimate and detect out of distribution data. And I'll talk about two works related to this problem. So to simplify things a bit, I'll be using this traffic sign classification as a running example throughout the rest of the talk. So if we take those traffic sign images and then fit the model using any off-the-shelf architecture using this data, Here we use softmax to denote this probability distribution among all the classes, and it's a vector that sums up to 1. And we define confidence to be the maximum probability among all the classes. So when a network converges, it would produce very high confidence for those traffic sign images. And this is actually not that surprising because networks trained with the cross entropy loss tend to amplify that. And to see this is indeed the case, here I'm showing you one example where we have a softmax prediction producing probability, say 0.8 for one of the labels, and then 0.2 for another label. And on the right side, we have the ground truth label vector, which is one hot vector. And this cross entropy loss basically calculates this negative log likelihood for this probability that corresponds to the true label, in this case 0.8. And as you can see, in order to minimize this loss, this probability has to go up to as close to 1 as possible. So you end up getting a 0 loss. So in other words, the goal here is to push this prediction vector S and this ground truth label Y to be as close, identical as possible. So this explains why we're observing high confidence prediction on the traffic sign data. However, during test time, let's say we're taking a completely irrelevant image, say a mailbox image, and then feed this to this neural network we just trained on traffic sign data. Now, ideally, we would hope that the network produce a low confidence score in predicting this as traffic sign. And because this mailbox image is sampled from a distribution that is not what the network was trained on, we call this out of distribution example or OOD example. And it turns out neural networks can be quite overconfident to out of distribution examples. And this is what researchers have observed in a series of experiments on modern neural network architectures. And to see this is indeed the case, here we sample a few images from this in-distribution traffic sign data. And for each of those, we calculate the softmax confidence, which is displayed here. And similarly, we do so for a bunch of out-of-distribution data and then calculate their confidence score. And if we were to plot this distribution of the scores that we just calculated, it looks like something shown here. So this green curve indicates the distribution for the training data, and the gray curve shows that for OOD data. And as you can see, these two curves tend to overlap a lot. So it's non-trivial just to draw a decision, draw a threshold somewhere, and then tell them apart.
Sharon?
Hello.
Quick question for Ms. Ramsey. There's just a question from the audience before you go on, perhaps. The question is, in the open world model, would the inputs that don't match what's expected be considered error or variance?
So this is a really good question. So if the input, let's say in our case, we just described, a bird image comes into a network that is trained on food images, this should ideally be captured as a red flag, which is an error. And if this is something that comes, let's say if it's a food image that looks visually different from our training data, and that is different from the scope of out of distribution that we're dealing with here. That's more of generalization. How do you train a model on a limited set of data and generalize to other data that is, have similar semantic meaning?
Great, thank you.
Great question. Thank you for that. Okay, so now let's move on. So now this question becomes, how can we distinguish those out of distribution examples where, it's distributionally distant away from your training data. And I'll first talk about this work, ODIN, which stands for Out of Distribution Image Detector. And this is a work we published 2 years ago, back at 2018, and now it has become one of the most commonly used OOD detection methods. So ODIN is comprised of two components. Firstly, we introduce this technique of temperature scaling. So temperature scaling was originally invented by Jeff Hinton et al. In 2015, which was used in this context of knowledge distillation. And it's actually a quite easy to use technique. So recall this is how we previously calculate softmax. Now we're taking this original output f of x and then scale this by a factor of t. And t is this temperature parameter here. And then after the scale, we calculate the softmax the usual way. So you might be wondering, why temperature scaling is useful here. Well, it has two important effects. The first is that it would push all these confidence scores to be closer to 1 over n. And here n is the total number of classes. Let's say if you're dealing with a 10-way classification problem, your confidence would be then shifted to closer to 0.1. And the second effect, which is more important, is that the distribution between this grain versus gray curve becomes more separable. So to see why this is the case, we can actually approximate the softmax confidence P of y hat, which is the largest output probability among all classes, using Taylor expansion. So when this temperature is large enough, we can focus on this first order. So the first order essentially measures, to what extent this largest output deviates from the remaining outputs. And if we were to plot this empirically, this is an example here I'm showing on a CIFAR 10 pre-trained neural network, which is indicated in red curve here. And then the rest of curves are out of distribution data sets that we considered. And as you can see, there's a clear separation between this red curve versus the remaining curves. So this explains why temperature scaling is a very useful technique in this context of OD detection. And in addition to that, we also introduced a second technique, which is input preprocessing. So essentially what it's trying to do is we take a test image and then pass this through this pre-trained neural network. And then we calculate this gradient of this loss with respect to the original input image. And so now we take this image and subtract this noise of magnitude epsilon, depending on the sign of this the gradient, and we end up getting this slightly perturbed image. So if you're familiar with how adversarial images are constructed, this is done in a very similar fashion, except for we are subtracting this noise, except for adding the noise. So the effect of subtracting the noise basically is to push the gradient in a way, push this input in a way that would reduce your loss. And by reducing the loss, you're effectively pushing this confidence to be even higher than where it was before, like this. So everything now overall shifted to the rightwards. And even more interestingly is the increment for those in distribution images is bigger than those out of distribution images. I won't dive into the details here due to time limit, but overall, this results in a bigger gap between the grain versus gray curve. So this kind of helps better distinguish those two types of data. Okay, so now we can put together those two techniques. And to put things in a concrete context here, we have a pre-trained classifier, let's say on this traffic sign images. And we take this pre-trained network and try to build an out-of-distribution detector G of X, so that you can, draw a decision boundary between this out-of-distribution and in-distribution data. And during inference time, for any given image, now we can calculate this calibrated softmax score on this slightly perturbed image X tilde, and then compare with this threshold delta. So if it's greater than delta, we think it's in distribution, and if it's smaller than delta, we flag that to be out of distribution for further inspection. So to alert, the practitioner. And delta is chosen so that a high fraction of in distribution images, let's say 95%, is correctly classified. And so this method really has two advantages here. The first is that it doesn't really require retraining your neural networks, so the parameters of your traffic sign classification model doesn't change at all. And therefore, you're able to preserve the classification accuracy on your original task. And so now we can look at how this detector is actually being useful in an end-to-end system. So now we're taking any input and pass that through a detector G of X. And for example, if this is a traffic sign, like a stop sign, it will then be routed to this downstream CNN classifier. And in contrast, if this is out of distribution data, this G of X detector would flag that to be OD and discard it. So to evaluate our approach, we take DenseNet, which was the state-of-art architecture back then, and then train on the CIFAR-10 dataset as in distribution.
Hey, Sharon.
Hi, Ramsey.
Sorry to interrupt again. I just have a few questions. And
sure, let's address those.
One's a long one, which I'll start with. I'm wondering about the actual definition of out of distribution. You've just shown here, for example, how different two distributions should be so that they should be seen as different. More specifically, in the real world, we almost never have seen training and test data that have exactly the same distribution. They might have, even if both are Gaussian, for example, they might have slightly different mean and variance, or the distribution of the collected seen test data might be only a subset of actual, which means seeing more test data and merging it with previously seen data might eventually lead to the same distribution of training data. Does that question make sense? It's also published if you want to look at the QA.
Yes, that's a really great question. So if we want to measure this, the out of distributionness in a more principled way, there are statistic tools that allows us to do that. For example, part of analysis that we actually performed in this original Odin paper is to adopt this notion of maximum mean discrepancy, MMD distance, as a statistical measurement for any given two data sets. And typically, this would, so what we found is actually a reliable metric that would tell you how close these two distributions are. And you can imagine if you were to split a CIFAR-10 dataset into 8 class versus the remaining 2 class and measure the MMD distance, that's going to be smaller than if you calculate this with respect to a completely kind of remote dataset like MNIST, handwritten digit datasets. Right, and what we found is actually as this distance becomes smaller, this out of distribution detection in general becomes more challenging and difficult, and which is expected. But thank you for that question. I think it's
great. And then quickly, people are asking about how do you decide on a proper T parameter to maximize the separation of the out distribution and in distribution? Maybe you're going to talk about that then.
Yes, that's a really great question. So in short, we do have this analysis. Unfortunately, I don't have the slides here, but the general trend is that as we increase this temperature parameter, we found the performance in terms of OOD detection accuracy tends to saturate, let's say after the magnitude becomes greater than 100 or 1000. So there is a curve that shows this saturation point. And in practice, you can actually validate this parameter on a separate, validation set and select the optimal parameter. But in general, it's not very sensitive to this temperature as long as it's high enough. So that's a short answer.
Great. So
Great
thanks.
question.
There's a few more, but I think we should probably go on for now. One thing we might do is just check in every, I don't know, 5-8 minutes and ask if there's questions, because otherwise I feel rude interrupting you constantly. So.
Oh, that's okay. Feel free to
Okay.
interrupt.
Okay.
Thank you for monitoring.
Yeah. Go
awesome.
ahead.
So I will proceed then. So now we're taking this pre-trained network on Sapphire 10 and evaluate on a subset of ImageNet as out of distribution data. So here's the results. On the x-axis, we show this false positive rate, which is a fraction of OOD images that are misclassified as in distribution. And on the y-axis, we're showing the true positive rate on in distribution. So as you can see, when the true positive rate is 95%, this red curve is the baseline using the raw softmax, and the blue curve is using ODIN, and we're able to reduce this significantly from 34.7 to 4.3%, which is quite substantial. And we thoroughly evaluated our approach on more out of distribution data sets, and we're able to show this consistent performance drop here. So this is certainly great, and ever since, there has been a lot of exciting progress made in this area, and here I'm just highlighting a few important works here. And among those, I'm particularly excited about this latest work on energy-based out-of-distribution detection, which is an approach that is both theoretically well-motivated and also empirically effective. So now let's dive in. To give you some quick background, this energy-based model is nothing new and has been around for decades. And Yan Lequin has this really nice tutorial written back in 2006. So effectively, an energy function would take in an input x, which is a high-dimensional vector with corresponding label, let's say y. And then this energy function would essentially return a scalar, which we call energy. And intuitively, this energy is low for observed data points and high for unobserved data points. And this energy is non-probabilistic in nature. So in principle, you can turn this into a probability density through Gibbs distribution. And so here, P of y conditioned on a given input can be calculated by taking the exponential of this negative energy and then normalized by this integral over all possible labels here. So here, this denominator is known as the partition function. And so if we were to equalize these two terms, we can express this free energy in terms of the negative of log partition function. And again, this is our trace back to the very classic physics notion. It's nothing new here, but you might be wondering, how this energy-based model is connected to neural networks. And it turns out a neural network trained on this supervised classification task can be interpreted from an energy-based point of view. So to see this is the case, we're taking a pre-trained model parameterized by theta, and then during inference time, we're taking an input, calculate the output vector, f1x, f2x, all the way to fy of x. And then we pass this output to the softmax function to get this normalized probability distribution. And this, you've seen this a lot already throughout this talk. This is how softmax is defined. Okay, so now if we define this energy to be the negative of this logit output, minus fy of x, this turns into this energy form that you just saw earlier. So now in this context of deep networks, we can actually express free energy by replacing this integral to be the summation over all this logit output because it's in discrete form, right? And now, during inference time, given any input x in this pre-trained model, we can very easily and conveniently calculate this energy using this log sum exp operation. And so what we're proposing here is to replace the softmax-based scoring function, which you already saw earlier, that produces overconfident predictions for OOD data, to be energy function. And here this x-axis measures the negative energy. We flip the sign of energy so that in distribution would have higher values and OOD data would have lower values, right? So overall, these two distributions now become much more reasonable. And in particular, if you look at this in distribution data, it no longer have the spiky distribution like we saw earlier. And it turns out this is a very appealing property of energy score, which I'll explain in a second.
Sharon? Sorry, I think these are some a little backwards looking questions, but maybe you could jump in on them before they get too out of date.
Sure.
I think one person was just asking about how this type of work of separating in or and out of distribution, how that works in the world of adversarial learning, and wouldn't an adversary really construct something so it looks to be in distribution?
That's a really great question. Actually, the third part of the talk, which I'll get to in a second, we'll cover that question. So yes.
Okay, fantastic. And then I think there was just a general question of like, how do you, for testing, how did you construct the out of order distribution? I don't know if that's more specific or not. But.
Yeah, that's a great question. So for evaluation purposes right now, a lot of this literature sort of take on this approach where we sample out of distribution from a completely different data set, where you can construct this from a completely different domain, different tasks, and so on, right? So that's kind of the standard evaluation that we're performing here.
Great. Okay, thanks.
All right. Thank you for all those great questions. So now let's move on. This is kind of my favorite part of this work because we're, finally are able to show something to really, to show this why energy is the right metric to use for this problem. So to see this, we can express the density function for a given pre-trained neural network using energy. So P of X. That's a probability of, a data sample. The data is sampled from certain distribution. In terms of this, so this numerator is exponential of this negative energy. And the denominator is taking this integral over this entire input space, right? So this in practice can be very expensive and intractable to compute, especially when we're dealing with a very high dimensional space with complex data, right? So the key observation here is that the lack of the normalization term actually doesn't affect this out of distribution detection because it's sample independent, right? So if everything is scaled by the same factor, the overall distribution remains relatively the same. And so it turns out this energy score provably aligns with the probability density of our training data P of X, right? So we can now show that P of X is proportional to this exponential of negative energy. And through simple derivation, we show that negative energy is proportional to the log likelihood. And this means energy is actually a very reliable measurement because any data with high probability of occurring would result in lower energy and vice versa, and out of distribution with low probability of occurring would lead to high energy. So that's the key. And in contrast, we're also able to explain why softmax confidence score is the wrong metric to look at, because essentially it doesn't align with this probability density. So we can actually show mathematically here, this softmax confidence score is proportional to the energy shifted by this maximum logit. And in fact, this maximum logit is in a completely different direction. So it's higher for in distribution and lower for out of distribution. And energy is, in the opposite trend, right? So when you add those up, it leads to this final outcome that is no longer proportional to the log likelihood, right? And then this explains, why we're observing such skewed distribution that is overconfident on out of distribution. So to evaluate energy-based approach, we take this network pre-trained on Sapphire-10 and evaluate on SVHN. So this is, an example where the OOD data is coming from a completely different domain, right? It's Street View housing number. And this is the energy score distribution that we end up producing. And you see the false positive rate is substantially reduced to 35.68. And more importantly, we observe that these two distributions now become much smoother and reasonable, right? It's no longer having this spiky issue. So this is certainly promising and encouraging. And we thought, this is kind of more evaluation that we performed on different OOD data set like places, texture, and so on. Okay, so this is so far so great, and we thought, can we do better? What if we were allowed to actually change or retrain this network? So maybe we can shape this energy surface explicitly so that the gap between, in terms of energy, between the in distribution and OOD can be further kind of enlarged. And this would, as a result, lead to stronger OOD detection performance. So we proposed this training objective displayed here. It has two terms. The first term is the standard cross entropy loss, which is trying to minimize the classification error on our original task, let's say traffic sign classification. And then the second term, which is new, is the energy regularization term. So what this regularization term is essentially trying to do is to control the energy on the in distribution images so that it stays, within certain margin parameter, let's say MN, possible. And then for those out of distribution data, we try to push this energy to be higher than the margin parameter, say M out. And I want to point out here, we're making this assumption of having access to some outlier training data, which are completely unlabeled and sample. You can imagine we can take some images, from the internet that is diverse enough, but these are not identical to our OOD test set. So we're not actually fitting our training objective to the test set. And this is something I want to point out here. So if we take this fine-tuning process and then measure the energy score afterwards. So on the right side is what ended up happening. And we can see that now these two distributions become even further, kind of separated. And we end up, reducing this false positive rate down to 1.18, which is quite substantial. And to measure on more data sets, recall this is what I've shown earlier, where the blue bars are for the softmax score and the green bars are using energy score. And when we're allowed to fine-tune this network, we end up producing false positive rate that is substantially smaller. And so here is a more kind of comprehensive comparison that we performed with other competitive methods in literature. And as you can see, energy fine-tuning consistently lead to improved performance, establishing new state-of-the-art performance on this challenging task. And another thing I want to put out here is if you look at this rightest column here, so we're also reporting the test error on the original classification task, which is cipher 10 or cipher 100. And what we showed here is this fine-tuning actually leads to, no worse or comparable test error on this original task. So overall, it achieves much better trade-off because you can do well on your original task and simultaneously kind of having stronger defense against those OOD data. So that's quite desirable. And some of the ongoing efforts within my group, including, we're right now exploring using energy-based methods for this OD detection in this multi-label classification setting, which is actually more common because if you're looking at taking a picture, more often a picture can contain, multiple objects such as a dog and a cat in the same image. And this is less restrictive compared to these multi-class classification that we've been evaluated a lot in the past, right? So this is a direction. And then the second, we're also working on developing theoretical guarantee and error bounds under some simplified data distribution, say a mixture of Gaussian. And lastly, I just want to briefly touch upon this important aspect, which is robustness of out-of-distribution detection. And in fact, one of the audience earlier on raised this question, right? So this is, where we're coming to. And this is joint work done with my amazing collaborators here at the UW-Madison and Google. So to motivate this problem a bit, what we've seen in the past is better and better out-of-distribution detection methods, which improves the accuracy over time. However, it's unclear, how robust these methods are that we're actually building. So, for example, we're thinking if by adding some small perturbations to an input and out-of-distribution data, like this, which is lying somewhat on the boundary, right, between these two types of data, would that actually change the prediction to actually fool this detector to be, producing the prediction of in-distribution? And if so, how can we robustify these methods? And to put things into, a situated example, let me, show you several concrete possible failure modes of OOD detectors. So this is what you've seen earlier when we're evaluating these images that are clean, intact, right? So let's say the stop sign gets routed, correctly to the downstream classifier, and then this mailbox gets rejected. So that's kind of a nice word that we have been in. However, you can imagine we might be able to add some adversarial perturbations to this mailbox image here. So to fool this OOD detector, G of X, so that it classified as in distribution. And then this would be passed to the CNN and trigger the downstream prediction and corresponding action taken by the car, right? So this is certainly undesirable. So adversarial example, can be constructed kind of in an intentional way by malicious users, but there's also another type of, perturbations that are naturally exist in this physical world that can be, added to your input unintentionally. For example, it could be motion blur that happens during your data acquisition, or it could happen due to the weathering issue like snowing, fog, frost, and so on, right? So these corruptions could change your input slightly as well. And so to view this a different way, effectively, this out-of-distribution image now across the boundary, right, to be on the other side, and then to be classified as in distribution. So we try to construct such adversarial attack on these common OOD detectors using the standard technique based on PGD attack, which was originally proposed by Madre et al. In 2017. So essentially what it's trying to do is, these blue bars are, let's say, the output on a clean image, and they were trying to modify this input image in a way that would induce the output to be somewhat closer to, let's say, 1 hot, which is very confident, like in distribution. So mathematically, it's equivalent to just maximizing a divergence between your output and a uniform probability distribution. So then we take these adversarially constructed examples and then evaluate on all these kind of common OOD detection approaches, including ODN. And what we found is the short message here is pretty much all these common OOD methods are fragile under such adversarial perturbations. So these green bars are, effectively having false positive rate close to 100%. So this is quite concerning. And in this work, we proposed this technique called ATOM, which stands for adversarial training with informative outlier mining. We try to mitigate this issue by building a more robust OOD classifier. So there are two components to this, as you can infer from the title. The first component is adversarial training, which is quite standard. And the training objective is provided here. It has two components. The first term is effectively minimizing the standard cross entropy loss. And then the second term is the adversarial training part on outlier data. So what we're doing here is to adding this additional K+1 class that would produce an OOD score, which is higher for outlier data and lower for in-distribution data, right? And then this adversarial training part is basically a min-max game that is searching for this worst case outlier data that would produce a very low OOD score, which means the loss is high on the second term. And then the entire optimization, try to minimize this worst case scenarios. And so we take this the first version of the training objective and train on CIFAR 10. This is, what ends up happening if we track how this OOD scores evolve during the course of training. And as you can see on this, basically we're taking the intermediate model snapshot from epoch 10, 20, 30, 40, and so on. So interestingly, what we observed is that the network actually quickly converges to solutions where it produces, very high OOD scores during the course of training, which means if you train this model for a longer time, you're probably, not learning that much because it already learns what these OOD data are. And this motivated this second component, which is inspired by this hard negative mining literature, where the key idea here is to choose outlier data where this network is mildly uncertain about. So in other words, we're being more deliberate about what outlier data we train this network on. Previously, we're just sampling uniformly from this auxiliary data set. And now we're, braining some of these tricky cases for the network to learn. So this figure on this right side gives you an intuition about what ends up happening. So this left side is when we're training uniformly on this auxiliary data set. And the decision boundary that is end up learned by this detector is somewhat loose, right? There's a lot of white space in between the outlier data and in distribution data, which is in the middle. And in contrast, by introducing this informative outline mining, we're able to have a tighter estimation on this decision boundary, so to kind of capture the difference in a more accurate way. And this turns out to be very effective in improving the robustness performance of these methods. So just to show you, these are the previous approach, and on the right side is when we're training with Atom. And as you can see, under adversarial attack, we're now able to reduce this false positive rate significantly down to 20.55. And even nicer, on the clean evaluation data set, Atom is also able to kind of reduce the error rates to 1.69. This is evaluated on CIFAR 10 pre-trained network. Okay, so to wrap up, I would like to recap on today's talk. So I first talk about this issue of out-of-distribution uncertainty estimation, where we show the softmax score suffers from overconfidence issue, which makes it less desirable for OOD detection. And this technique, ODIN, helps mitigate this issue to some extent by calibrating the softmax confidence score, and that improves the detection to some extent. But ultimately, this energy measurement is a promising replacement for softmax-based OOD scores, and that leads to kind of a very promising performance in practice as well. And in the second part of this talk, I've also touched upon this robustness issue, where we show pretty much these sort of methods are very fragile under adversarial perturbations and common corruptions. And robust training with this new approach, Atom, can substantially improve the worst case performance. And there's still, a lot of exciting work that we can develop in this space by developing kind of better algorithmic approaches for OOD detection. But more importantly, let's, think from a holistic view, right? I think ultimately what we're trying to aim for is this reliable end-to-end machine learning framework in this open world. Now, this is currently, a lot of this machine learning pipelines are developed in this real world where we have training data, and then train the model, deploy the model. There's no such end-to-end loop that formed, right? And everything, if you change your data or class labels, you have to start all over again. But in the future, what we're envisioning, is this end-to-end loop as the users keep uploading the new data stream to this platform. We'll have this input validation module that can, first, distinguish if there's something, belongs to some new semantic class, or if there's something that belongs to your existing semantic class. So if those, new classes are being detected, we can then kind of form this loop by performing class incremental learning on these newly detected classes. And for those new examples that belong to your existing classes, you can actually, try to train a better, improved model of it by incorporating those more data. And it will be interesting to also analyze, from this end-to-end point of view, how reliable our system actually is. So that's all I've prepared for today. And with that, I would like to, thank you for organizing this great event, and thank you for, being here and staying, throughout this whole talk. I'm happy to, take any remainder questions that you may have.
Hey, thanks, Sharon. And I'd like this virtual crowd to stand up and applaud for you. And you can imagine the rousing ovation from around the world, wherever people are watching from.
Thank you.
I don't know if people are clapping. So, but great job, thank you. So I think maybe we could, there's a few questions we could go through, if that's cool.
Yeah, let's do that.
Here's a recent one. What's the performance of directly combining traditional algorithms which deal with adversarial samples with Odin? I don't know if it's easy to answer that question.
That's an interesting question. So unfortunately, I don't have the numbers for that particular setting. So this would be actually, okay, I see. Just to perform adversarial training on the standard classification network and then evaluate on Odin. Unfortunately, we haven't done that experiments. But my hunch here is that the performance wouldn't be as competitive as what we showed in this Atom paper, because what's happening here is in Atom, we're training with this kind of auxiliary data. Let me go back to the slides. So you're actually leveraging this more information from not just in distribution data, but also outlier data to have a more accurate estimation on this decision boundary. So what's going to happen is that the decision boundary in this Atom is more accurate than if you were to simply train with the in distribution data. So if you're interested, I highly encourage you to look at this full paper. We have this very comprehensive comparison with almost all the prominent paper methods in literature. And we actually have some theoretical proof that shows by leveraging this auxiliary data, you're able to kind of reduce this error bounds to some extent. So that's the general response I can.
Great. No, that's really helpful, and I think the table shows how much work you have to do just to publish one paper in the machine learning world these days.
The students is incredible. I have to give credit to the students.
Yeah. So maybe one more, and then I'll just say one more thing. What is the main difficulty when working on multi-label classification?
That's a great question. So as you can imagine, when we're dealing with this multi-class scenario, often each image is associated with kind of one prominent prediction, right? And that's kind of the intuition we rely on when we're devising this kind of Odin or softmax-based approach. But in this multi-label setting, the difficulty here is how you can actually consider a metric that jointly consider all these informations from different labels. So in fact, in this current work that we're going to submit to ICLR this year, a key contribution there is to actually propose this aggregation mechanism to combine those, let's say, the score metrics from individual labels, kind of in a way that allows you to separate out in distribution and out of distribution. So that's kind of one of the key difference and challenge there.
Great, thank you. Let's just do one more. It's a little bit lengthy, but I'll just read it to you. For adversarial out of distribution defense, it seems like a high order OOD data problem. More specifically, I'm thinking you can train the network to, I think it's really asking about, like, can you get into a situation where you're essentially always kind of escalating, like you kind of put a defense in place, but then the people kind of take advantage of that and craft a more clever, adversarial inputs. And kind of, is it one of these, in security, sometimes we solve problems, and I think sometimes it's just a racket where we kind of continue pretending to solve problems. So how do you see that in this world?
I think that's definitely, a concerning issue, and unfortunately, this is kind of one of the very, early works that we set out to do in this literature, really trying to, start to think about what are some of the approaches that allows us to kind of devise more secure. And as you can imagine, what we're evaluating here is the simplest scenario, right? Under this infinity bound, norm bounded attack. But there are more sophisticated attack out there that could break all these methods. So that's kind of, I see that as a more, consecutive questions that this work currently can open up to. And we'd be kind of excited to see, what the community has, come up with in the next.
Yeah, great. Thank you. So, just to summarize, here we are in this system seminar, and I think the one way to think about what you're doing is, anytime we're deploying machine learning in systems, there's always this question of, like, did we train on the right stuff to make it, the thing that we're doing now, make any sense? So I really think this way you're thinking about, whether something's in distribution or out of distribution, is really going to be a very central piece of how we think about deploying machine learning in systems very broadly. So, so thanks for that perspective. I also wanted to share with people that this talk is being recorded. We'll make it available on the MLOS seminar site. And, I really appreciate everyone coming here, and I really appreciate Sharon giving this fabulous talk. Thank you again, Sharon. And we'll
thank
see
you. That's a really well kind of a summarization on the takeaways.
Oh, sure. Oh, of course. And yeah, thank you again, and we'll see you all next week.
Thank you, everyone.
Thank you very much.